Okay, today we want to go over Lab 9, a multifunction calculator without using an ALU. This is basically an implementation of the ALU described in example 4.12. I want to go through that example to help you design your ALU. Notice that our design will have 4-bit inputs, whereas the example in the book had 8 bits. If we take a look at the example, we see that we have this idea of an ALU that we could design here with 3 switches indicating which of the functions that we have. The value of the switches determines which function we're going to implement, whether it's A plus B, A minus B, A plus 1, and so forth. And so we see we have 8 different functions that we can implement. The values of A and B are handled through the switches. Here we have, for the example, 8-bit inputs for A and 8-bit inputs for B. If we take a look at this idea of, rather than designing each individual component, what we're going to do is we're going to have an extender. The extender handles the function for each of the bits. So notice here that because A and B are both 8 bits wide, we have 8 extenders. If we take a look at our extenders, we see that we're going to use an adder just like we did in our previous labs where we had an adder and a subtractor. We had an adder that handled both addition and subtraction. We're going to do the same thing here, but rather than addition and subtraction, we want to be able to do all 8 functions. Okay, so taking a look at some of the designs from the ISE, we see that here is our adder, our eventual adder that we're going to feed in the values of I sub IA and IB. IA and IB, each 4 bits wide, are going to be fed into our adder. Notice that the adder has the adder inputs are coming from this extender, which is 4 bits wide, and we have into the extender our original values A and B. And so we want to make changes to this extender to handle all 8 of the functions. The extender is a symbol that's made up of a bitwise extender handling each of the bits. We have 4 AB extenders to create this extender symbol, and then the output of that symbol is fed into the adder. All right, let's talk about what's inside of the extender. We know that the extender has to handle all 8 functions. Taking a look at each of these functions, notice that we have 0, 0, 0 is an arithmetic function, A plus B. 0, 0, 1 is an arithmetic function, A minus B, and so forth. Here we have our extender. We have, as I said before, each extender handles 1 separate bit, and each extender inside has each of these functions, these 8 functions. Addition, subtraction, plus 1, just A directly. We may just want to feed A directly through our adder to give us A plus 0. Here we have A and B, which is a logic operation. Here we have A or B, A exclusively ORed with B, and A not. So just looking at it more closely, it physically describes what each value selection of X, Y, and Z are. Here, if you want more practice, you can look at one specific example that was given in the book, the values of A, the values of B, and what the expected outcome would be for each function. All right, so now we want to look inside of the extender. Let's just take a look at the addition operation. Here we know that if X, Y, and Z are all zeros, we want to have A plus B. We know that we are feeding into our extender for one extender. Let's say we're doing A0, we would have A0 going in, we would have B0 going in, and we want to do A plus B. Notice here, because there are 8 functions, within the extender we're going to use 2 8 to 1 muxes. 8 to 1 muxes, the select lines are X, Y, and Z respectively for both of the muxes. I sub 0 for both of the muxes are going to handle A plus B. Notice here, if we have A, we have B, we know the outputs of these are going into the adder, so that would give us A plus B. Let's take a look at one of the other examples. Each of the I/O lines are going to handle an individual function. The I0 line handles A plus B. What about one of these logical operations? Notice here we have X, Y, and Z are 0, 1, 1, which is I3. We want to do 1, 0, 0, which is I4. We want to do A ANDed with B. So the way we're going to do that is we're going to let I sub A be A ANDed with B, and we're just going to have this B mux be ground. And so here we've done our logic operation, A ANDed with B, and then when we add it together in the adder, we're just taking the output of that and adding it with 0. And we know anything added to 0 is just going to be itself. A ANDed, A plus 0 is just A. So here is our A, here is our 0 going into the adder, and we have A plus B. Right? So for each of these other inputs, you need to come up with the values. If it's 0, 0, 1, we want to do a subtraction. We know how to do a subtraction. If it's A plus 1, we may want to set our, our A input equal to A, and we want to have our B input be equal to ground, to 0. And so then we're adding together A plus 0. And so you want to step through each of these and handle the inputs into these muxes. Again, this is what the inside of one extender is going to look like. You're going to have 4 of these, 1 for each of the bits of A and B, and then these are going to be fed into. This is going to create a component. You have one extender, you're going to have 4 of these, 1 for each bit. Then you have a symbol that is 4 bits wide, your extender, which goes into your 4-bit adder. And so then at the top level, you're going to take your ALU, and then you're going to put it through an 8-bit register so that you can store the value. Okay? That's the end.